Thank you all for coming today to the AWS Loft here in San Francisco. My name is Jeremy Bendout. I'm with a premier consulting partner called Corp Info. We're actually based down in Santa Monica, but are up in San Francisco and have clients up here. And we're really excited to host you all today for this Aurora event. To my right, we have KD Singh, who's from AWS. He's a solutions architect, and he's going to be speaking a little bit about Aurora. And then we have my friend Advait from GoGuardian, CTO and co-founder, to tell their story, which is really cool and exciting. Without further ado, I'm going to pass the mic over to KD.
One quick correction. Jeremy said I'm going to talk a little bit about Aurora. That's wrong. I'm going to talk a lot about Aurora. I have 45 minutes. That's a lot of time. So let's get started. My name is KD Singh. I'm a solutions architect with Amazon Web Services. And welcome to the Aurora session in SF Loft. So what is Amazon Aurora? Amazon Aurora is enterprise-grade, MySQL compatible, ACID compliant relational database system built for the cloud. One of the key objectives when we were building Aurora is to get rid of the performance and availability issues in existing commercial databases and do it with the cost and simplicity of a traditional open source kind of a system. So we designed Aurora to be MySQL 5.6 compatible with InnoDB engine. So a lot of your existing applications would work out of the box with it. And for new applications, or in case you have to migrate things away from your existing databases, we have some cool tools and features that I'm going to talk about as well. So let's take a quick history lesson. So relational databases, they have been around, 40 years, 45 years, something like that. And when they were designed, there was no cloud computing, obviously. So they were designed for on-prem environment. And if we dig deep down into what a database actually is, at some level, in a very simple way, it is some compute and storage bundled together. There are different layers of functionality in a relational database. We have the SQL layer. We have the transaction layer, we have caching, and we have logging. But all of these layers of functionality are typically bundled in a single box. A single box is where all of these are. And then we need to scale databases. If you have worked with databases at some point, it's painful. You know what I'm talking about. Scaling databases is not easy. It's easier said than done. The simplest way to scale a database is to do vertical scaling. Just scale it up. You have a small box, just buy a bigger box. You run out of space or the performance is not good enough, you just buy a bigger box and then a bigger box. As you can imagine, at some point, you'll hit the ceiling. There is no bigger box to buy. So in that case, vertical scaling would no longer work, and you'll have to look at horizontal scaling or scale out techniques. You mean physically hold it? Oh, wow, these are too many things to manage. All right. So at some point, you have to look at horizontal scaling techniques or scale out techniques. And over the years, people have gotten good at horizontal scaling to some extent as well. So this slide shows you 3 of those popular techniques. The first technique is to shard databases. What this essentially means is you do a horizontal partitioning of your data. You divide your table up horizontally, and you put part of the data in one node. You add another node, and you add the remaining data in the other node. And if you have to shard further, you split the data further, and you keep adding more nodes and moving data to them. As you can imagine, if you want to write a query that needs access to all of your data, which is typically the case, you'll somehow need to figure out where your query needs to go to get your answer. And for simple sharding, your application has to take care of how the query is split, where the query is going to get its results, etc. So it's not easy. Developing applications with sharded databases is not easy. and you still have issue with respect to data loss. If a node goes away, how do you get to the data again? So there are still some issues. The next version of things, or another version of doing it, is called shared nothing, which is the similar concept. You still split up your database and you put data in different nodes. But here your application does not have to worry about writing the query in the right way. This thing is handled by the SQL layer. So the complexity is now in the SQL layer, but the issue of data integrity and data and node going away still remains. So it's somewhat better, but it still has issues. And then there is the shared disk kind of horizontal scaling solutions, which actually do a much better job with this. Oracle RAG, for example, leverages something like this. In this case, they essentially fuse the caches together. So caches are fused together, which means you have a single storage interface to work with. So things are a little bit better, but in this case, we run into issues like, again, nodes going away is a bad thing, but then things like hotkeys or hot partition or distributed locks. So there are a whole set of problems that come with these techniques as well. So this is what was happening for the last 30, 40 years. But let's just think, if you had to design a relational database today, what would you do differently? What would you design? You would actually try to design something in which you don't have to worry about horizontal scaling like that. You don't have to rely on vertical scaling, and you don't have to worry about the sharding and shared disk and all of that, managing all of that yourself. So you definitely want something that can scale out and scale out seamlessly. Push button scaling is what you want. You want something that is self-healing. You don't really want to care about how many nodes are running my database behind the scene. You don't have to worry about what if a node goes away. You want something that detects failures and something that can self-heal. It can recover from those failures on its own. There is a lot that needs to be done to accomplish that. I'm going to go over those things, but that would be a requirement that most of DB people would have, I'm sure. And then you want a database system which can leverage other modern cloud-based services, like the services that AWS platform offers. So you want something that out of the box works well with other services in the ecosystem. And with this short requirement list or wish list, what you will end up designing or building is actually something very close to Amazon Aurora, which is why we built it. So let me talk about some of the technical details of Aurora. This is the Aurora picture. So what we essentially did was, let me get out of the way. What we essentially did was applied service-oriented architecture principles and design patterns to databases. No monolithic blocks with layers of functionality running on a single box. That's an anti-pattern, because there is too much dependency, too much state on that system. We want decoupled systems. Decoupling sets you free. Once you have decoupled system, they can scale very nicely. And the notion of service-oriented architecture is independent functionality in your system is bundled together as a service. And there are different services in your solution architecture that all talk to each other. So you can talk to a service and get a well-defined functionality out of it, like a black box. It's a black box. You want something from it. You want caching functionality in your database. There is a service handling that. There is not a single service handling everything. Multiple services handling different part of your functionality. And so we did that. So we are looking at the same monolithic block. So we have SQL, transaction, caching, and logging tiers. But what we did here was we moved caching and logging out of that monolithic block. They are their own thing. There is a different service managing them. Once you do that, you can now scale much better. So what we do is your storage And caching is essentially a separate service within Aurora, managed by Aurora. I don't even know it exists, but I'm just opening the hood and showing you things a little bit. So we take the storage out of that stack, and then we create segments. We create 10 gigabyte segments. When you set up Aurora and you want some storage out of it, we set up segments, 10 GB of them, and we 6-way replicate those segments. Each 10 GB segment replicates 6 times across 3 different availability zones. I'm going to assume some baseline AWS knowledge here, so let me know if you 3 availability zones. Yes. So if you don't know what availability zones or regions are, I can talk to you later. I'm here after that. But within an AWS region, it will make 6 copies of your data across 3 availability zones. And then it's going to scale automatically. When it sees that your needs are now beyond 10 GB, it's going to add more segments to your database automatically. You don't have to go to console or CLI or do anything about it. It's going to do it for you. And then it actually leverages, it backs up your data automatically. It's incremental continuous backup of your data into Amazon S3. S3, as most of us would know, is the simple storage service which is designed for 11 nines of durability. It stores data in a very cost-effective manner. So Aurora is going to back up your data for you, and it is self-healing. It's going to detect if any of the nodes or segments, nodes or volumes in your database are corrupted in some way. If it detects failures or corruption of data, it's going to create another copy, or it's going to heal your system for you. You don't have to worry about healing as well. And then it leverages other AWS services very effectively. For example, it uses the Amazon DynamoDB services for it's a key value NoSQL service. Actually also does document store, but it's a NoSQL database service, and Aurora leverages it for metadata storage. It can, DynamoDB does a good job with high speed and performance. So metadata in Aurora is stored there, and then it leverages Amazon's simple workflow service to orchestrate the whole workflow related to Aurora. It's managed by SWF, and for DNS, it leverages Amazon Route 53 behind the scene. So it essentially, with this picture, you see how the service-oriented architecture concepts are all coming in, created different services, and we have functionality handled by different components separately. And once this decoupling is there, you can scale much more seamlessly. We have seen rapid adoption of Aurora. Aurora was actually announced in November of 2014 during reInvent, and we were in beta for quite some time. It was made GA July of 2015, so 10 months ago or something. And since it was made GA, we have actually, it's been very humbling. It has seen very fast adoption. It has now become the fastest growing service in AWS history, which is saying a lot because there are, I don't know, 55 different services. So this is the fastest growing. So we have seen rapid adoption. Rapid adoption is one thing, but we have seen its adoption across different verticals. We have seen all the way from business applications to IoT applications to web applications to search advertising and different verticals like edtech verticals. We have a cool customer from edtech. Advert is going to talk about their use of Aurora. But all kinds of verticals, all kind of applications, games, media, they leverage it now. So let me give you some examples to give you a sense for who is using it and why they chose to use it. Maybe it will give you some idea about how you can leverage it as well. The first one I want to talk about is Expedia. We all know Expedia. It's a big travel portal. They actually operate in 70 different countries. I did not know that, but they have 150 sites, 70 different countries. So they have a ton of data in what they call their travel marketplace. and data has great business insights, as we know, the whole big data analytics field. So they want to run real-time queries to gain business intelligence from all their data from their customer and from the customers and what they're booking and where they're booking things. And they were actually using Microsoft SQL Server. They were not very happy with its cost. It was turning out to be very costly for them. I see some smiling faces. So you know what I'm talking about. And the other thing was the performance as their travel marketplace data was expanding quickly. The performance was not up to the par. It was not scaling well. So they looked at a few solutions to replace their SQL Server based application. And for example, I think they tried Cassandra with Solar Index, but they figured out for the amount of RAM they need, the number of nodes they need is a lot. So performance is good, but cost is still a lot. So they did some due diligence on what's the right database solution for them, and they ended up choosing Aurora. The thing with Aurora is it seamlessly scales from 10 gigabytes, as I said, but it goes all the way up to 64 terabyte. So it scales, and the performance scales with it from 10 GB to 64 terabyte, 64 TB. So they were, for example, able to get 20,000 inserts per second. You want to write a lot of data. They were able to accomplish 25. This is in a steady state. The peak was 70,000 inserts. So that's a big number. And the response time for their queries was in milliseconds, 17 milliseconds for 1 month worth of their data. We are talking about a truly global enterprise with international presence. So this is what they were able to accomplish with Aurora. And then some more examples. Thomas Publishing. This is actually over a century old company, and they were using Oracle for their production database. They had similar pain points. They had rapidly growing volumes of data. They don't have one business. They have multiple businesses under that umbrella, and they had rapidly growing data sets as well. Their main thing was if the huge amount of upfront investment they had to make to get a bigger database system, to put it on-prem and to buy licenses. The CapEx was just too big to their liking. So they also leveraged Aurora. With Aurora, the pricing model is the typical Amazon pricing model. There is no upfront cost, and it's pay as you go. It's on demand. There is reserved pricing as well. I'll go into that. But with Aurora, they were able to get the right price point that they liked, and the performance was great as well. So they replaced their commercial database with Aurora as well. And another cool thing is that there are tools in the ecosystem. I'm going to talk about them. We have the schema migration tool that converts your existing schema from a system like Oracle or SQL Server or any other Postgres database system, and converts into a schema that's compatible with MySQL 5.6 InnoDB engine, which is what Aurora is. Schema conversion tool, and then there is a database migration service that migrates your data from on-prem or from EC2 or from another database sitting somewhere else and brings it into Aurora. So with these tools in the ecosystem, they were actually able to migrate the whole stack within 4 weeks without any downtime. So it was a big win from them. Two more, Alfresco. Their whole thing is in document and content management, and they wanted to scale to millions of documents, actually billions of documents, and they wanted a very fast response time. And with Aurora, they were able to scale to 1 billion documents with a throughput of 3 million documents per hour. So the performance is really very good. The way to get performance, one of the ways to get performance, I'm going to talk about performance next, is to leverage read replicas that Aurora manages for you, and you can have up to 15 read replicas that you can provision with Aurora. And it's not just people with traditional commercial enterprise databases that are leveraging Aurora. We have some customers who used to be MySQL customers, for example. They were open source. They were, for example, Safe Software and Double Down, which is in the gaming industry. They were MySQL shops. They used Aurora, and performance. Aurora is designed to perform 5 times faster. That's according to our test, it performs 5 times faster than MySQL running on similarly configured hardware. So performance is there, and for commercial databases, it should be 1/10 the cost of a typical enterprise commercial database. But open source software is free, right? But even those people found cost savings when they moved to Aurora because they had to provision less hardware to get more performance. So even those customers, for example, these people save 67% and 40% of their costs by migrating from an open source software into Aurora. All right, and Aurora is fast. I've said that many times, but let's do some benchmarking and find out how fast it actually is. So what we did was, and we keep doing it, is we used MySQL sysbench benchmark, which is pretty much industry standard in this space, and we ran some tests on it. And the write performance, we were able to get more than 100,000 writes per second, and more than 500,000, actually 585,000 reads per second from Aurora. This is with 4 client machines consuming data off of Aurora, and each of the client machines doing 1,000 connections each. So we are heavily loading Aurora, which is sort of necessary if you want to get big numbers. But we heavily load Aurora, and we were able to get 585,000 reads per second. This is a big number. Not too long ago we were talking about a couple of thousand reads per second as pretty good. So this is quite nice. Actually, you can, if you want to do experiments on your own, you can get to these numbers yourself. So we published a paper or a guide on how we got those numbers. So you can, in your AWS account, spin up an Aurora instance within minutes and do your experiments. So we provide you guidance on, for example, your client machine should be in the same VPC. Your client machines running on EC2 should be the higher end EC2 instances, so that network bandwidth is not a bottleneck. You have to tune your Linux. We tell you how we tune the Linux to get to those numbers, etc. So you can run this. You can search it and get to it, or the slides would be available later on. But the more important thing is this also shows you some of the best practices that you can follow to get good performance out of Aurora as well. So it's a good guide to go through. But running experiments in a lab environment is one thing, but real world conditions most of the time don't mimic lab environments. In a real world environment, you'll have multiple users running queries of all kinds, some optimized, some dumb, and they are all contending for resources. So you have user contention in the real world that you have to deal with, and then your metadata. It won't typically fit the data dictionary cache. It's going to overflow the buffer. So so you have to worry about that. Your data won't fit the buffer cache in a real world scenario, because you have too much data, or you're querying too much, so the buffer gets evicted. So you have to worry about that. And last but not the least, if you have an enterprise database, which is the backbone of your company or your enterprise, you cannot run a single box with database on it. You cannot run a single instance. You want fault tolerance, you want high availability. You don't want your database to go down. So you have to worry about fault tolerance in the real world as well. So towards that end, we ran more experiments so that we can figure out how Aurora is doing in the real world. The first experiment was about scaling user connections. So we went from 50 connections all the way up to 5,000 connections. Again, it's sysbench benchmark that we are leveraging, and their OLTP workload. As we scaled from 50 to 5,000 connections, user connections, Aurora performed pretty well. The performance did not degrade. It actually increased as the number of user connections increased. But we compared it to what MySQL running on EC2 would give us. And Aurora performed up to 8 times faster than MySQL. The MySQL box, so we did not cheat. The MySQL box we set up to compare against is probably the biggest MySQL box that we can run, that we can get in Amazon right now. So we provisioned 30,000 IOPS so that the IO performance is good, and we used a good instance. I think we used the I2 instance types to run the experiment, and we did everything in a single lazy in the same VPC, all of that, but still Aurora performed much better. And the next one is, what if the metadata does not fit the data dictionary cache and it gets evicted? To mimic that, we scale the number of tables. We increase the table count so that metadata size increases and it no longer fits in the cache. In this experiment, we went from 10 tables all the way up to 10,000 tables with 1,000 connections. And in this case, Aurora on an average performed 11 times faster. So here we compared Aurora performance against 3 different kinds of MySQL configurations. One was MySQL running on RDS, the relational database service, the managed DB service that we offer. The other one was we leveraged I2, 8 extra large instances. And the I2 family of EC2 instances is the high IO or IO optimized instances. I2 8 extra large has 32 virtual CPUs, it has 244 gigs of RAM, and it has 800 GB SSD drives on a single EC2 instance. So 1.8 terabyte SSD instances, single drive. So it's a very powerful machine, one of the most powerful machines we can offer. And we installed MySQL in 2 ways. One of those ways was using RAM disk, so that we are doing things out of memory as much as possible. We have lots of memory in I2 8 extra large. But in all cases, Aurora still outperformed MySQL. I'm going to get into why it does all of this. I'm just giving you some data points right now, but it did that. A key observation from these experiments is that I/O is not the bottleneck here. It's not as if Aurora I/O is so much better that I/O bottleneck is causing MySQL not to perform well. It is more than that. It's things like log sharding and the MySQL algorithm, the database algorithm it uses itself and how it's set up that is causing the problems. We'll look at some of those problems. The next one was, what if your data does not fit the cache and it overflows the cache? So to do that, we configured the database with 1 gigabyte of data, and we scaled it all the way up to 1 terabyte of data. So we just added a lot of data in the database, and we looked at what happened. 1 GB is not much database. Pretty much all commercial databases, your buffer cache is going to be able to hold it or a lot of it. But as you scaled, Aurora performance scaled with it. RDS performance did not. After about 100 gigabyte, Aurora performance started falling because data size became just too much, but your MySQL performance degraded much worse. So Aurora in this case performed 67 times. I'm not talking about percents here, I'm talking about times faster than similarly configured MySQL. And just to make sure that our engineers were not optimizing for the Sysbench suite, we ran the same experiment on Cloud Harmony TPCC, which measures throughput numbers, and there we did even better, 136 times faster. And the last experiment I want to talk about is the real world scenario in which you want to run in a highly available manner, in a fault tolerant manner. If you want to run in a fault tolerant manner, what that typically means is you need to have standby of your database or read replicas of your database at the very least. Read replicas in MySQL don't give you high availability actually, because you can't really promote read replica directly like that. But even if we look at read replicas, and we So when we added read replicas to the Aurora system and to the MySQL system, and we increased the number of updates from 1,000 per second to 10,000 per second, the lag that we saw between data getting synchronized in the read replica. There is the primary instance and read replica. We make updates to the primary instance. We figured out how much was the lag before that data was available in read replica. That lag in MySQL went from a few milliseconds at 1,000 updates per second to over 300 seconds. 300 seconds of lag for your data to go from your primary database instance into your replica. And on Aurora side, the lag did not increase much. It's because of how we designed the storage tier, but it went from about 3 milliseconds to about 5 milliseconds, so negligible increase. So how did we achieve these results? I'm going to spend the next 5 or 10 minutes talking about that. The bottom line is you either need to do less work or you need to be more efficient and do it more smartly. To scale database performance, everybody does optimizations related to database algorithms and log sharding, etc. But beyond those optimizations, you have to make sure you don't do too many IOs because IOs can kill your performance. And you have to make sure that the network, you don't have too many packets going over the network. A high-end system like higher-end EC2 instances can do 1 million or 2 million packets per second, but still it's a constrained number. You have to worry about how many packets you're pushing over the wire. And you have to do asynchronous processing. You cannot do context switches, and you cannot do synchronous processing because that's going to kill performance. Different parts of your system waiting for each other to finish the job. That's performance killer. So let's focus on these 2 or 3 things. Doing fewer IOs. So on the left side of the picture, you see MySQL, and there is the primary instance of MySQL right here, and then there is a standby instance. And here we show when you write to MySQL, what happens. The different kinds of things that MySQL has to store are shown in the bottom. It has to do redo log records. It has to worry about bin logs, about the actual data that it needs to push. Double write buffers is a technique that is specific to MySQL, but they make sure that in case of a crash, your ACID properties don't go away, that you still have consistent data. So it has to worry about redo logs, bin logs, data, double write buffers, and metadata FRM files. The different colored arrows represent all these kinds of data.
Some people may say that Amazon purposely has made MySQL implementation inefficient. Since they have MySQL as an open source, they can easily make MySQL as efficient as Amazon Aurora. How do you combat that statement?
So the contention is Amazon is cheating. My answer is no. MySQL is not an Amazon product. It's an open source project. So this is how.
MySQL the way Aurora is done, because you could bypass EBS and other stuff. You could use the lower level architecture similar to this. Or we can't.
You can. So the question is, if we were to re-architect MySQL and not use EBS, can't we do that? Yes. So AWS services, we like to eat our own dog food. For example, Aurora is using DynamoDB. Aurora is using Route 53. Aurora is using instance SSD stores. Aurora is using SWF. You can leverage all of those services to get something like this on your own, but it's not easy. If you have a huge team and your business goal is just to run your database in a very nice manner, then go ahead, do it. But most of the people out there would consider it undifferentiated heavy lifting. I don't care about setting up a database. I worry about what goes on it. That's what solves my business problem. That's where my money comes from. So yes, the features that you can leverage to perform your database better, and you can implement other databases like Cassandra, and people do that and get good performance out of AWS or Mongo or so yeah, you can do it. But if you take a vanilla MySQL running on AWS it does a lot of different writes. For example, it has to write to EBS volumes, all these different kinds of data. And when you write to EBS volumes, a copy is made between EBS volumes through the EBS mirror. And then you write it to the standby instance, all of this data in the other AZ, and then the changes are propagated all the way back down to the mirror EBS volume and go back. So before your read is or your write is committed, a lot of different steps have to happen. And some of these are not asynchronous. Some of these are synchronous. So there are bottlenecks inherent in how the vanilla MySQL is implemented, right? In case of Amazon Aurora, as I said, you see these 6 different boxes. We replicate your data 6 ways, and you see 3 AZs across 3 different AZs. And the key takeaway from this slide is the storage layer that we created for Aurora is not just a dumb block store. It's not just dumb storage where you write things. It has the smarts to do computations as well. For example, in MySQL, if you want to do redo logs in a database, your database box has to do redo logs and write it to storage. In Aurora, you don't have to do it. You give the redo logs to the storage tier, and storage tier is smart enough and competent enough to replay the redo logs on its own. So it's taking some of the compute load off of the database tier and doing it in the storage tier. Because of this better functionality in the storage tier, and then it does automatic backups to S3 as well. Because of it, it's able to perform much faster. I have to be careful about time, but the next thing I'm going to talk about is high availability. If your database performs really well, performance is really good, it's great. But unless the database goes away, if it crashes, then your performance is of no use. So you have to make sure that it's fault tolerant, it's highly available. And again, as I said, 3 different AZs, 6 copies of your data, and it's a quorum based system. We don't wait for all the 6 storage locations to say yes, I have the data. We have a quorum based policy. Some of them, I think it's 4 out of 6 say we have it, then we proceed. And then behind the scene they have a peer-to-peer network where these storage units are smart enough to talk to each other to figure out what their current state is, if somebody is missing something or not. So all of that happens asynchronously within the storage tier without the compute part of it, the database part of it, having to worry about it at all. And then it writes backups to S3 as well, which are continuous. The next thing is for high availability is survivable buffer caches. If your database crashes and your buffer crashes with it, in a typical traditional system, that's what happens. If your box crashes, the cache crashes with it. You have to now, when you are ready to recover from your crash, you have to bring all the data back in because your cache is no longer there. So you have to read from disk just to get your data back. So there is to recover from fault, it takes a lot of time. It can take minutes or hours depending on what your last checkpoint was and how much things you have to replay and how much data you have to read from disks. In case of Aurora, your caching is separate from your DB tier. Even if the DB tier crashes, your cache is still warm, it's still there. The instance comes back up, even if a new instance comes back up, it can go to the buffer and get warm data and just start from there. I just mentioned that in a traditional database. So what we typically do in a traditional database is we checkpoint the data. And over these 30, 40 years, people have experimented with what a good checkpoint duration is. 5 minutes is a reasonable number. You may have more or less, but 5 minutes is what the checkpoint duration typically is. And so in the event of a crash, you go to the last. You have the last. You have to. You get your last checkpointed data in, and then you see what transactions happened after the checkpoint state. That's what the redo logs do. You have to replay the redo logs to get to the current state. You get the checkpointed state, you have the data. Now you figure out what changed after that last checkpoint. You replay all of those actions again, and that's how you recover. In case of Aurora, it's continuous backup of your data, number one, and replication is 6-way. And to recover from crash, you don't have to do anything different. Even in the default case, when the DB tier goes to storage tier to get to data, the storage tier is going to look at redo logs and see if something changed or not. It's going to replay redo logs anyways, even if there is crash or no crash. So it is doing its normal work, even in the case of a crash. So the performance difference in recovering from a crash is non-existent for Aurora. And finally, this shows some timelines of how we can recover from a crash. In Aurora, it typically takes a minute or 2 minutes, including DNS propagation, to recover from cache. And in case of traditional MySQL, it can take much longer, depending on what your checkpoint was and how much redo you have to do for recovery. The next couple of things I'm going to talk about is the ease of use. So if you want to scale your compute on Aurora, you can go from there are different type of, if you know AWS and EC2 instances and RDS instances. Aurora is a database engine within RDS. So if you're familiar with RDS, it will be very easy for you to start using Aurora. It's the same kind of interface. And you can start with a RDS instance, which is not very powerful, maybe 8 cores and 32 GB RAM, something like that. And then you can, with a push button from the console or from your application or from the API, you can scale the compute part of it and go all the way up to R38 extra large, which gives you 32 cores and 244 gigs of RAM. So vertical scaling is very straightforward. And in terms of horizontal scaling, again, there are segments 10 GB each, and it's going to scale automatically in 10 GB increments up to 64 terabyte worth of data. So it's very easy to scale. Then using CloudWatch service, if you're familiar with it, we have a lot of metrics, both about Aurora and about the SQL you're running on top of it, that we push to CloudWatch service. So using CloudWatch metrics, you can get a graphical interface or your data of how things are performing in your system. And you can also set up CloudWatch alarms and get notified. For example, if your CPU is loaded more than 80%, notify me. So CloudWatch is integrated. I think more than 50 different system and OS metrics are captured, and you can get to them very easily and set up alarms, etc. And then it's a very secure system. It by default runs in the Amazon Virtual Private Cloud VPC service. So network isolation is there, and all the goodness, network goodness that comes with VPC in terms of security groups and subnetting and all of that is part of it. If you want to encrypt your data in transit to Aurora, it has SSL enabled endpoints. So you can do SSL encryption of your data in flight to Aurora using AES 256-bit keys. And for your data at rest, Aurora also encrypts that data. And to manage your encryption keys, you can leverage the Amazon Key Management service, which manages your encryption keys. So again, it works very well with other services in Amazon ecosystem. And it is, so this is going to be quick. It is offered as a managed service. As we were discussing earlier, yes, you can, if you have to run a database in Amazon, not only Amazon, anywhere, whether it's on-prem or anywhere, you have to do all of this. You have to worry about your data center and powering things, and somebody in your team would do racking and stacking, installing operating system, patching operating system, installing software for your database, then patching it, and then backing up, snapshotting, et cetera, et cetera. And then, comes the real DB admin work of query optimization, schema design, et cetera. So you have to take care of the whole stack. You run it on EC2, like I was saying earlier, a part of it is handled for you. You don't have to worry about where it's running, racking, stacking, installing operating system, patching operating system. the EC2 service takes care of it for you, but you're still responsible for all these gray blocks. Yellow is taken care of, gray you still have to worry about. And if you use a relational database service, RDS for Aurora in this case, then much more is taken care of for you, including backup and snapshotting, et cetera, even scaling and fault tolerance, high availability is taken care of you. You worry about what actually is beneficial to your business, which is app optimization, schema design, query optimization, et cetera. So it's undifferentiated heavy lifting essentially goes away with something like Aurora. And then it's very cost effective as well. With Aurora, you start at, I think, 29 cents per hour for our smallest instance. And that's on demand. So you use it for 1 hour, you pay 29 cents, and you walk away. That's your monthly bill. That's the bill you pay. But if you reserve capacity with Amazon and commit to using Aurora for 1 or 3 year period, the reserve pricing kicks in and the prices go down. The 29 cents now become 10 cents an hour. So it's very cost effective, no upfront costs. And then with reserved pricing, you can save 44% or up to 63% with 3 year reserved instances as well.
If I subscribe to your Aurora service, do I have to separately subscribe to S3 and the Route 53, or it's part of the whole package?
Right. So the question is, what does this 29 cents per hour cover, right? So we meter your usage very closely about all the things because we want to be very fair about your usage and you get charged accordingly. As far as S3 is concerned, the backup that comes as part of Aurora, the default backup it does is included. If you do additional snapshotting, you can do it at any point. Those additional snapshots, we'll meter it and charge you for it. You don't have to worry about provisioned IOPS or anything. The storage itself is covered, but there is a IO charge. And any data going from RDS out of Amazon Cloud, there is a data transfer out charge as well. There is no data transfer in. So those are the 3 pricing components.
Were you suggesting in the previous slide that there's 2 levels of service, one where you manage to showing the launch goal? So is this the way it works, or is there some in-between pricing thing that you can parsing to manage it yourself? Is this an option as well?
Yeah, this is things running on EC2.
Yeah. And how much do you save by getting additional service, or what's the price difference between those 2 slides?
So the question is, if I were to take the pain of installing it on my own on EC2 and managing all of it, how much money can I expect to save versus leveraging Aurora? And the surprising answer is, in most cases, you'll be spending more money doing it yourself on EC2. I'll give you an example.
Yeah, to pay somebody to do it.
Not pay somebody. Even at the technical level, I'll give you an example. Yes, you end up paying more because you have to have additional people in your team dedicated to doing that. But even technology-wise, let me show you. Let me give you an example. So this is if you were to use MySQL running on EC2 and you were to manage a lot of it, installing MySQL and all of it, you would have to, in this case, I'm using an enterprise case. So there's a primary instance, there is a standby database instance. You're using R38 extra large, and you're using EBS volumes, and then there are 2 replicas, read replicas for better performance. Now let's see, it comes to around $23 per hour in this case. And let's now look at Aurora. In case of Aurora, you'll have 1 primary instance, and then you can have up to 15 read replicas. But for similar configuration, you only set up 2 read replicas. It shows you your total cost for running Aurora, and it comes to around $18 per hour. So you save around 20% running it on Aurora versus yourself. But the key thing to remember here is MySQL performs worse than Aurora. Aurora is 5 times faster. So you can probably use lower level instances on Aurora and still get similar performance. So instead of R38 extra large, you go to R34 extra large. Your performance likely won't suffer. You get similar level of performance like your MySQL on EC2, but your costs go down, and now you're making 50% savings. on top of running it on yourself on EC2. One thing I quickly want to highlight here is that it looks straightforward and simple here, but there is a lot of technology and a lot of expertise that is required to handle these workloads. And we have even after you decide to use a higher level service like Aurora, things like migrating to Aurora, things like app optimization and schema optimization and query optimization, you can do it yourself or you can engage with AWS partners. So we have a whole ecosystem of consulting partners. We'll hear from Corp Info a little bit later today about the things they offer. So if you think this is not your core competency, you don't have good DB admin teams, etc., you can still tap into AWS partner ecosystem like GoGuardian did and get help to accomplish this as well. All right. So this is about costs, and the last part is about migration. And I think Jeremy is briefly going to talk about this as well. The first service here is called the database migration service. This service helps you migrate data into Aurora. You specify your source database, which could be sitting on AWS in EC2 or RDS, or it could be on-prem in your data center. And then you give it your target Aurora instance, and it's going to, number one, get all your data into Aurora. And once the data is in, it's going to then start replicating changes from your source to destination as well. So it migrates your data, and then it keeps on replicating. What that essentially means is your application does not have to go down, even because data is in, replication is happening. So late one weekend night, you can do DNS switchover to Aurora because the database migration service was replicating your data at all times, and it can also replicate to and from Redshift as well. And this is two ways. It's not just about bringing it in. You can take it out. It's heterogeneous, one to another. And then we have a schema conversion tool. So two things here. One is migrating from one database to another is not easy. It's really difficult. The fact that there is a tool now that helps you automate a part of it is actually a big win for this field. It seems trivial, but it is not. Different databases, they are like entirely different things. And that's number one. So this is, I think, a very good start. It's actually giving you something to start with. And the number two thing is any AWS service that has been launched till date or would be launched, we launch it as a minimum viable product, which is solid with good functionality. But after launching, we listen to feedback like this on what do users really want. We don't want to build things that nobody actually has a good need for. So we listen to feedback, and then we quickly iterate. So I'm pretty sure you'll see new features coming from the database migration service tool soon, and hopefully it will meet your needs better. Or talk to Corp Info as well. They can help you. Anyhow, so and schema migration tool, if you have things like views or stored procedures or DML, the kind of statements in your database system, converting from one schema to another is not easy. The schema migration tool is a development environment. You download it to your desktop, and it tries to migrate as much of your schema as possible. It won't succeed 100% of the time because it's not easy. There is the users I've talked to typically see 80% of their schema migrated very well. And for the other part that it's not really able to migrate for you, it's going to highlight the part of the schema that it was not able to migrate and give you suggestions on what you might do about it. So it's a big win and helps people a lot. And the last thing I want to say is we also offer SQL functionality so that you are able to test your Aurora instance as well. Using SQL, you can insert artificial faults into your Aurora instance to mimic things like database nodes failing or disks failing or issues in the network. So you can insert those faults and see how Aurora performs, and this helps in your dev test as well. With that, thank you for your time.
So, my name is Advait, and I'm the co-founder and CTO of GoGuardian. We're a company based down in LA. We started about 2 years ago. And my cousin, he's 11 years old, and his name is Soham. He lives in New Jersey, and he has a Chromebook that was issued to him by his school. And it's this little laptop. It's really, really inexpensive. And instead of having textbooks at the beginning of the year, instead of having textbooks at the beginning of the year, he has this Chromebook. And all of his interaction with school happens through this device. So that's like reading in class, assignments, exams. He submits all of his work through Google Docs. And to me and probably everyone in this room, it's kind of like stunning, because education, as we know it, is really, really transforming. And it's kind of fundamentally changing. And from an educational administrator perspective and a teacher perspective, we have all of this new technology that's coming into the space. And it's really, really disrupting the way students are taught. And it's sort of a daunting experience. IT administrators at schools now have to deal with tens of thousands of actual devices. And a teacher in a class has to deal with 30 laptops open. And I think a lot of these people really need help. So at GoGuardian, we provide tools to help these people understand exactly how these devices are being used, and provide tools to help them actually manage them at scale. We're down in LA. We're on about 3 million student devices right now across 3,000 school districts in the US. And we're just growing really, really, really fast. And we started about 2 years ago, to give you guys a sense. So from an engineering perspective, what I'm here to really talk about, and like the crux of our scalability problem, is really around timestamped events. So we do a lot of things, but really this is the meat of our data scalability issues. And by timestamped events, I mean whenever a student does anything on a Chromebook, we collect an event, a payload that has a bunch of metadata, and the metadata has a timestamp. And we're ingesting lots and lots and lots of these. I think as of now, we're doing about 100 million of these a day. Because students are only in school during a very fixed amount of time, we have a very, very cyclical workload. So when East Coast and West Coast schools are on at the same time, this amounts to about 6,000 events per second that we're ingesting. And so we kind of like really, really had to struggle in the early days to re-architect our systems to be able to deal with this massive, massive influx of data. So we started about 2 years ago, and Google GCP didn't really exist in its current form 2 years ago. Even if you look at their offerings right now, a lot of their stuff is in beta. We're really, really happy that we went with AWS for a lot of the stuff that I'm going to talk about, but primarily around Aurora. So I did a talk in LA that was really, really just focused on our use of Aurora. I wanted to broaden the scope for this talk to give you a little bit more context about how we adopted it and why we adopted it, and in general, some of the more like data like pipeline principles that we're using. In this 2-year journey, I've learned a lot about data architecture and stuff like that, and I think that a lot of you guys that are dealing with scalability issues are going to learn a little bit of interesting stuff from here. So we have 26 Aurora instances right now, and counting. Across all of them, we're probably have around like 12 terabytes of data. We're ingesting 100 million events a day, things like that. So the last talk I gave, I had a bunch of hand-drawn diagrams like this, and it was pretty controversial because some people really loved them, and other people like really, really hated them. But I really enjoyed drawing them, so I'm just gonna. I drew a bunch of diagrams. So let me know what you think after the talk. So GoGuardian started off as a side project of my co-founder, Asa, when he was back in college. And I'm going to throw him under the bus here a little bit, but he decided to use this design, primarily with PHP as like a monolithic application and MySQL as a monolithic data store. And as GoGuardian started to scale, especially in the early days, this arrow from PHP to MySQL was just really a problem. Very, very early on, we learned this general principle, which I think is very applicable across, like whether you're dealing with data storage or whatever, amortization of fixed costs. So let me go into what exactly I mean by that. So if we go back to this slide, here we have a Chromebook, and they're submitting data to event data to a PHP application, which is then transforming it and then eventually writing it to MySQL, right? So in order to perform this one unit of work, and by unit of work I mean inserting this event into MySQL, there's a number of fixed costs that are associated with just performing that work. And I consider these fixed costs like actual like ceremony. They're like not really useful things, but you kind of have to do them in order to make things happen. So by that I mean like incoming TCP, TLS negotiation, HTTP request parsing. PHP itself is fundamentally stateless, meaning that between 2 consecutive requests, you can't really share any state without some crazy hacks. So you have to initialize all that state. Because it's also stateless, you have to negotiate a database connection, and then the actual network round trip for performing that database work. So all that stuff here is on the left in red. The incremental cost is what I feel is like the actual work that's being performed. So in this case, it's the transformation of the data, so it's suitable to write. And then it's the actual query execution in your data store. So our principle was, how do we like take this large amount of fixed costs associated with performing useful work and amortize that across many, many things of useful work. So in this diagram, I have just this block. It's like 1 unit of work being performed. The total cost is that, and the incremental cost is like the actual work being performed. So a very naive way to get this amortization of fixed costs is with batching. So we control the client-side business logic of these Chromebooks. So what we could do is have them buffer up data in RAM, and every minute or so flush that buffer, so you're performing sending multiple events per HTTP request. And that kind of looks like this. So on the left here, you have the 1 unit of work use case. On the right here, you're performing 3 units of work. So at face value, it looks like the total cost has increased, which it has. But as you continue to add more and more of these green rectangles, you're performing more real work, and this red box becomes mitigated as you scale. So I've kind of been intentionally not using database terminology here, because this is really truly a general principle that I think is applicable in a lot of use cases. So in our use case, we had to buffer on the client side, and there were obviously some trade-offs in terms of liveness of data. If you're waiting a minute before you flush, then customers don't get to see that data for a minute or so. But depending on your application's use case, you guys can make that call. For us, we didn't really have a choice, and we really had to. Lesson 2, understand your system's throughput versus concurrency relationship. So this is kind of a really subtle one that I've only recently grasped fully and like really formalized. And I'm hoping like you guys can kind of see the power of what I'm about to describe to you. But a lot of people describe systems throughput in isolation. They say that this database can perform 10,000 writes per second, or this system can handle 100,000 reads per second, things like that. But really, these like in a concurrent world, these operations are actually happening in parallel, so at the same time. And in order to maximize the total amount of throughput in your system, you have to perform work at the same time. And there's actually a very, very interesting relationship between concurrency, like parallelism, like the work that's actually being executed at the same time, and throughput, which means the total amount of work that's done in a unit amount of time. And that relationship kind of looks like this. So down here at the bottom, so here, the x-axis here represents concurrent connections or parallelism or whatever. And the y-axis here represents total throughput. And the red graph kind of represents what I think is the relationship between these two. So at the bottom left here, you have, as if you have 1 unit of concurrency, then you're only able to perform 1 unit of throughput. As you increase your concurrency, you start to get more and more throughput. So as you perform more work at the same time, you're able to do more work total. But up here, you start to get some really, really interesting properties. At some point, you're performing so much work in parallel that the actual management overhead of dealing with the parallel work that's being performed starts to really become a factor. And you start to see this peak throughput. In our use case, when we were using vanilla MySQL on RDS before Aurora was even a thing, we found this to be 200. So around 200 connections, we were maximizing our throughput. And the really, really bad part about this is that as you increase the throughput thereafter, you start to see, as you increase the concurrency thereafter, you start to see this severe drop in actual application throughput. And when we were kind of doing postmortems early on, we didn't really understand this relationship. And in retrospect, it seems really, really obvious. But I think that when you're designing your applications, you really need to understand this and really optimize for this sweet spot here. So MySQL, we saw this at around 200. I think KD had some slides that demonstrated that Aurora was significantly higher. With our applications use case, we're seeing a sweet spot in the high hundreds of active connections to an Aurora instance. And obviously, Aurora is our throughput that we're getting through Aurora is way higher. And I have slides later to describe that. Another thing that kind of was a factor for us is PHP statelessness. So because it's stateless, you have to initialize a database connection for every request that comes in. So as the number of HTTP requests that you're processing concurrently increases, the number of database connections that you're holding open also increases. And it really, really pushes you that way along this x-axis until you start to kind of go over this peak, and then the actual database requests start to slow down, and which increases the latency of your HTTP requests, which increases the total number of HTTP requests that you're handling at the same time, which further pushes you down that way, and it causes a lot of downtime. So there's a number of things that you can do to prevent this. The most obvious one is use connection pooling. But what I'm really, really trying to convey here is that based on your application, based on the systems that you're using, this graph has very different shapes. For example, Aurora doesn't really have this death cliff at the end. And the slope of it is very, very different than the MySQL one. So it's important to just really understand how that works for you guys. So some of you guys may know MySQL has like a synchronous protocol, meaning that you can only have one in-flight request at a single time. Other protocols like HTTP2, for example, you can keep a single connection open and multiplex various request responses. Yeah. So about 200 units of work happening at the same time was our peak. Cool. So lesson 3 for us was unthrottled access to a throttled resource is bad. And I think that that's relatively self-explanatory. Here, we didn't really have any control over this arrow on the left. And although we could control the actual business logic of these Chrome extensions, we couldn't stop our sales team from selling and stop our product from actually growing. So we didn't have fundamental control over this left arrow. And that means that we didn't really have control over this arrow. And based on that last graph, you guys can kind of figure out what happened. So we needed some mechanism to actually throttle this arrow without dropping data. So we evaluated a bunch of queuing systems, and we settled on Kinesis. It's very, very similar to Kafka in that you essentially get an ordered stream of records, and that stream is sharded based on some shard key when you insert. And you get to read that stream asynchronously, independent of your writes afterwards. And the important detail here is that it does act as a true buffer. So if the writes over here start to slow down, or you get a huge burst of events on, huge burst of events on this arrow, Kinesis really, really acts as a safeguard that blocks against these. Another really, really sweet win was that we got to use this thing called the Kinesis client library, which is a Java library that Amazon offers that deals with checkpointing and dynamic load redistribution. it's really, really sweet. So all you have to do is implement your business logic, and it'll scale up and scale down as needed. In terms of amortizing your fixed costs, this model also had another huge win, where we were able to pull thousands of records off of the Kinesis queue at a time. Instead of having to deal with the HTTP request scope, you can kind of broaden your scope and think about hundreds or thousands of HTTP requests at the same time, pull them off all together, and then flush them to the database in one go. So it greatly increased the amount of amortization we were able to perform. Kinesis also had a really, really awesome side effect that we weren't really hoping for initially, but it allows us to like really decouple our applications. And our initial use case was just this over here, where we were inserting into MySQL, or Aurora really. But we found that you could have multiple readers, like stream readers, that read off the Kinesis stream independently from each other. And they maintain their positions in the queue independently. So if one slows down, it doesn't really propagate to other queue or other readers. And you're able to do really interesting things like spin up experiments to store data in an experimental data store, or filter the event stream and send out emails. You could do all sorts of things, and it acts as a great way to decouple your applications in that sense. Our final lesson was that Aurora is really awesome. So it was announced at reInvent 2 years ago, and during that time we had the PHP MySQL diagram architecture. We've long since graduated, and we have like dozens of services. But back then, when we heard the announcement, we had 2 engineers, and we couldn't have celebrated like more, except it came out 6 months later in July, which was like the most painful waiting process in the world. But we use Aurora in production a lot, of course, and I don't really have any contrived examples about Aurora usage. Like these graphs are not really benchmark driven; they're like real service, real world usage driven. And I don't really have an agenda to push Aurora either, although it may seem so. So this graph is the amortized insert latency per row. There's 2 lines here. The blue line that's kind of basically the same as the x-axis is the median latency, and the red line is the 95th percentile latency. So we have this application outfitted with metrics, and as you can see, we did a DNS switch to Aurora right around here. And although the median latency, which is the blue line, didn't really change at all, the 95th percentile latency of inserts severely dropped from like tens of milliseconds to like 1.8 milliseconds. So I think that this is a property of Aurora which isn't really advertised enough. A lot of people talk about the throughput, a lot of people talk about the amount it scales, but I think the consistency with which it delivers its performance is a win that is really understated. If you can bring your 95th percentile latency down like this, it definitely has really positive effects. Here's another graph on the read side this time. Red line again is 95th percentile, blue line is median, and as you can see, the 95th percentile reads drop way low. Sorry? Yeah. I think, yeah, absolutely. It's really wins all around. And the final one, which I think is really interesting, is, so this, I took a snapshot yesterday of all of the read replicas that we have in production, and the y-axis here is the replica lag. So each line here represents a read replica, an Aurora read replica that we have, and you can see that almost none of them go above 25 milliseconds, and the x-axis here is a period of like a week. So in the MySQL world, you kind of have to really architect your applications around this constraint of read propagation delay. And you have to do all sorts of crazy hacks to like write to caches at the same time as you write to your masters to avoid situations where you're reading stale data. And I feel like you don't really get to embrace the horizontal scalability that read replicas provide. And with Aurora, because of this, it's like so fundamentally different from MySQL propagation, like vanilla MySQL propagation delay, that it allows you to architect your applications in a really different way. And I don't think that that's really stated enough. Like people say that at face value that the replication lag is low, but I don't think people take the next step and say, what does that actually mean as an application developer? What sort of things can I do now that were not possible? So another point that I wanted to make is that at the time, this was about a year and a half ago. At the time, we were evaluating a number of solutions because vanilla MySQL wasn't working for us. So we were looking into Elasticsearch and Solr and Cassandra, and we only had 2 or 3 engineers at the time. And we just didn't have enough expertise to handle like a full-scale Cassandra deployment. And I think that we made a really wise decision to really stick with what we knew in terms of operations. Like we knew how to handle a MySQL instance, we knew its failure modes well, and we had a really clean upgrade path to Aurora. And in retrospect, I'm really happy with the decisions that we made. So in summary, here's the 5 main things that I've learned. Amortize your fixed costs. Understand your system's throughput versus concurrency relationship. Unthrottled access to a throttled resource is bad. Use queues to decouple applications. And Aurora is really awesome. Thanks for listening. We're doing some really interesting stuff. As you can see, we're operating at pretty significant scale. Our engineering team only has about 20 or so engineers right now. Last week, we launched this product where, so we're on about 3 million devices, and I think that really gives us this opportunity to have a 30,000-foot view of how education is actually happening in America. And it's a very interesting perspective. We launched an application, or launched a product last week called GoGuardian Director, which gives administrators a view of the educational applications that they're actually using in their district. And I think that this has the potential to actually give visibility to these people who have decision-making power and actually bring about this technology transformation that I think is so obvious and so necessary in schools. So if you're interested in dealing with lots of data and actually having an impact on education, come chat with me afterwards. And if you like this stuff, let's grab a beer afterwards. Any questions?
Yeah, how much does it cost a school per student to maybe discount the Chromebook acquisition?
Yeah, so our costs, it depends on which product you use, but on average, it's about $5 a student a year, or in that ballpark. Like the device itself costs about $200 to $300. So compared to that, it's very manageable. Yeah. Mm-hmm. Cool. Yes? There's a lot, actually. As you can imagine, obviously the barrier to entry to create a new web application today is like minimal. And we're really seeing, like 5 years ago, like nobody had a laptop in class that was open, right? Whereas now it's like, I think the majority of actual schools operated in this way. So there's dozens and dozens of actual ed tech applications available. We're really agnostic to what those are. We just want to provide visibility and help schools understand what the best schools are using and what they should be modeled after, essentially. What do we do from a developer perspective? Yeah, so it's binary compatible with MySQL, right? So from your application's perspective, if you're communicating with the MySQL server or you're communicating with an Aurora instance, it's completely agnostic to that, right? So you can do whatever you need, really. And if you want to run local MySQL in a Docker container, that totally works. So we have about 12 terabytes. We're ingesting, I think, 100 million events a day times 100 bytes. I can't really do math off the top of my head. But what we ended up doing is actually sharding our Aurora instances. So we have this unique property where 2 separate schools, we don't have the obligation to query data from across those 2 schools. So we can segregate that data, and it makes for a really natural shard key. So we have 7 Aurora shards dedicated to storing this event data, and based on which school you are, your data ends up in one of those shards, and we have the ability to horizontally scale that way. So I guess if a single school had more than 64 terabytes of data, we'd be in trouble, but I think we would have bigger problems then. We made a very interesting mistake about doing a schema change and like data format change at the same time that we did a migration. So don't do that. You should just keep your data the same or separate these two and do them separately. Our process involved using Spark to pull data out of our old MySQL instance, performing the actual data transformation. We also did sharding at that same exact time. So then separating out the data into the individual shards and then loading data in. It was a very, very long and lengthy process, but this was back when the data migration service didn't really exist. And we haven't had an opportunity to play with that because all of our high volume data stores are Aurora to begin with. So at the end of the day, MySQL is like an ACID compliant OLTP data store, right? And if you're doing large volume OLAP analytics, there is sort of an impedance mismatch. We have no need for transactions really. We're not a bank, so if we drop 0.001% of our data, it's not really that much of a problem. So although Aurora has scaled with us really, really, really well, we haven't fully taken advantage of it and all of the wins that it has to offer. So in that sense, I don't really regret anything, but I think that there may be an opportunity to use different data stores that more match our use case because we're not really using any of the ACID stuff.
Again, thank you all for coming. Katie and Advait were both amazing. And now I'm going to tell you a little bit about my company, the company that essentially organized all this. I'm sure you got some emails from Amanda, as well as some of the AWS reps that are here. But Corp Info is what's called a premier consulting partner for Amazon Web Services. And what that means is that we are in the top 1% globally to help accelerate companies just like yours so that you can move faster from a strategic standpoint, from just some ad hoc consulting to actually providing additional bandwidth to your organizations so that you can get some of this work that was described by Advait and some even things that you're thinking right now. We can provide those resources to you from a leadership perspective or from more of a boots on the ground perspective where you're like, I have this vision, but I just don't have the team to get it done. We come in and we help make that happen. So to give you a little bit of background about our organization, we have 50 plus AWS certifications. We've migrated over 70,000 servers over the past 2 years. We've also gone through what's called an audit by AWS to provide managed services. And what that means is we had a team of people from Amazon that said if these guys are going to be working and managing and helping to monitor clients of Amazon servers, we want to make sure that they have a process that's oriented in the way that Amazon considers best practices. So we went through the audit, we passed with flying colors, and we now have a whole service dashboard and monitoring tools that we give to our clients as a part of that offering. We've actually been around since 1983, so we've been reborn several times over the years as technology has changed, and the latest sort of rebirth has been with AWS, and we've been one of the fastest partners to reach premier status. To give you a sample customer list, and I'll go into a few cool stories, we're all over the board as far as the types of organizations that we work with, from enterprises to startups. Even with Advait and GoGuardian, it was even just a few hours where they came in and said, we have this idea, we just want some initial consulting. So we're willing to help invest and make things happen for your organization so that you can get things done. So if you want to chat about that, feel free to meet with myself. We also have Caleb and Romy from our organization here. But to tell you a few cool stories about what we've done. So everyone see the Star Wars movie that came out back in December? So when those tickets actually went on sale, movietickets.com's website crashed because there was such high demand for the people that wanted to see the movie that their on-premise servers couldn't handle the load. And so they actually reached out to us and AWS and said, hey, if we were to migrate into Amazon, can you provide us the confidence and the infrastructure that we need so that we can support this mass scale event, which is the biggest movie in the past decade? So we actually did a complete migration of years of movietickets.com's infrastructure over the course of 3 weeks so they could get to the next sale when the movie was actually in theaters. So that was one cool success story. That's these tickets right here. We also did a really cool Super Bowl campaign for Samsung. And that was where every smart TV was going to be sending some cool features during Katy Perry's halftime show. And what we did was we actually did all the load testing for them and helped to revamp and re-architect their AWS infrastructure, specifically leveraging CloudFront to help test for 500,000 concurrent connections per second. So during the big game, they were able to make sure that it went off without a hitch. And then some of these other diagrams that we do, we're constantly monitoring our clients for cost and looking for ways to save them money. So I know that the AWS bill can get big fast sometimes. Usually that's also a correlation to your success, because that means people and customers are using your services. But there's other opportunities for us to actually leverage, simple things like reserved instances. And there's actually a whole RI strategy that it's something that's talked about, but I feel like we can evangelize a little bit more on that. So buying within certain types of families allows you to scale up and down. And then going through things like right-sizing your instances. So we'll go through that. And then our bread and butter services are migrations into AWS, migrations into AWS Aurora, which I'll get into shortly, and then also re-architecting your application. So hey, we're in Amazon, but we're still thinking about our systems right now as if they're just a VM. And as we all know, there's so much more than that. So again, to just emphasize, premier consulting partner. There's multiple levels of partners within the AWS partner ecosphere. We just happen to be at the top. So to get into Aurora right now a little bit, we've actually helped a number of our clients migrate from MySQL into Aurora, which is pretty seamless. But there are many other databases out there, and you might want to try and take advantage of Aurora. So typically when we come in, we'll actually do a review of your entire AWS environment. So current region, that's key. Right now, Aurora does not exist in the NorCal region. It's only available in Oregon and in Virginia. So just knowing that right out the gate is something where if you want to take advantage of Aurora, make sure you're in the right region. And then going through just from the bottom up, every step from the foundation all the way up to the top. And then once we get into actually looking at the database, we'll want to look at overall performance today. We want to be able to give you some of those numbers that Advait was able to show earlier. If we can show you like, hey, this is the performance we can expect, and here's where we were, and here's where we're going, that'll obviously lead to success and hopefully some transformation of your company and your database performance as well. For the migration roadmap, when we're identifying various pieces of it, looking for the scale at which we're trying to go, that'll help for the cost optimization piece, because there are a number of different instance types that you can run Aurora on. Overall management, security. If you're a healthcare organization right now, Aurora is on the fast track to go through the BAA process, but it's not there yet. So just knowing little pieces of information like that will help you be successful. When we go through your database pain points, things that are existing there today, if we're going to maybe revamp a few things within that, we want to go through that and make it as, I want to say, a synergy process, so that your organization has the confidence that once we step away, you guys are left in good hands and you're well architected. So again, there's additional AWS resources. I'm sure you guys, if you're in the loft, you're spending a lot of time working with Amazon every single day. And literally, that's all we do. That is what we live and breathe at Corp Info. And just again, want to thank you all for coming here today. Let's get some beers, some wine. Oh, and now you have your survey, or did you put it in here? Okay, so now we're going to actually raffle off an Echo. Where's my trust assistant, Romy? She hates me right now. So she's going to reach in here, and she's going to pick out a name. Alex Litvak from Build Zoom. Congratulations. There you go. Awesome. Thank you so much. That was fun. All right, guys. Thanks so much again for coming. Looking forward to chatting with some of you, and have a good rest of your day.